Aging is often described as the cumulative effect of cellular damage over time, much of which stems from oxidative stress, an imbalance between the production of reactive oxygen species, RLS, and the body's ability to neutralize them. While oxidative stress is harmful in excess, it also plays a signaling role in processes like autophagy, the cellular cleanup mechanism essential for maintaining metabolic balance and longevity. Autophagy depends on a finely tuned redox environment. Too little ROS and the system lacks a trigger. Too much and it stalls due to damage to key autophagic structures like lysosomes and membranes. In this context, antioxidant vitamins such as C and E do not merely act as passive defenders against oxidation, they actively shape the redox environment in which autophagy operates. Their modulation of oxidative stress becomes a determining factor in how effectively cells engage in autophagic repair as we age. Vitamin C, or ascorbic acid, is one of the most potent water-soluble antioxidants in the body. It directly scavenges superoxide, hydrogen peroxide, and other ROS, preventing these unstable molecules from attacking DNA, proteins, and lipids. But beyond this protective role, vitamin C contributes to the regulation of autophagy through multiple pathways. One mechanism is its influence on iron metabolism. Vitamin C enhances the reduction and absorption of dietary iron and supports the activity of iron-dependent enzymes, including those that contribute to lysosomal acidification. Proper lysosomal pH is critical for the breakdown of autophagic cargo, and without sufficient vitamin C, this final step in autophagic flux may be impaired, resulting in a backlog of damaged organelles or proteins that should have been cleared. Especially in aging cells, where lysosomal function naturally declines, vitamin C can help preserve the degradative capacity essential for effective autophagy. Vitamin E, a fat-soluble antioxidant, provides protection where vitamin C cannot, in lipid membranes. Cellular membranes are especially vulnerable to lipid peroxidation during oxidative stress, and this includes the membranes of mitochondria, the endoplasmic reticulum, and autophagic vesicles. During autophagy, double membrane structures called autophagosomes form and fuse with lysosomes to degrade their contents. Vitamin E stabilizes these membranes, ensuring that they remain intact and functional under stress. It also influences signaling molecules like protein kinase C and NF-B, which play roles in both inflammation and autophagy regulation. With age, membrane integrity becomes more fragile, and without adequate vitamin E, the autophagic process can be disrupted by oxidative damage at its most structural level. Thus, vitamin E safeguards not only cellular lipids, but the architecture needed for autophagic transport and fusion. Together, vitamin C and E also work synergistically to regenerate each other. After neutralizing ROS, vitamin E becomes oxidized. Vitamin C can restore it to its active form, extending its antioxidant capacity. This interplay enhances cellular resilience during metabolic challenges, including calorie restriction, intermittent fasting, and mild exercise, all known to induce autophagy through low-level oxidative signaling. In such contexts, the presence of these vitamins does not suppress autophagy, but ensures that it occurs within a controlled oxidative environment, limiting collateral damage and promoting successful turnover of cellular components. Rather than acting as blunt instruments that cancel out fasting benefits, antioxidant vitamins can refine the process, helping cells adapt without being overwhelmed. Emerging research suggests that chronic low intake of antioxidant vitamins may impair autophagic flux in aging tissues. For instance, animal studies show that vitamin E deficiency leads to the accumulation of damaged mitochondria and protein aggregates, hallmarks of impaired autophagy. Likewise, low vitamin C status has been linked to defective collagen recycling, mitochondrial dysfunction, and greater susceptibility to oxidative damage in stem cells and neurons. These findings indicate that even marginal deficiencies, when sustained over years, may diminish autophagic efficiency and contribute to the cellular hallmarks of aging. As such, adequate antioxidant intake over time may not just slow oxidative damage directly, but also preserve the body's capacity to clear it through autophagy. Still, dosage and context matter. High-dose supplementation of antioxidants, particularly during active autophagy triggers like prolonged fasting or high-intensity exercise, has shown mixed results. In some cases, excessive antioxidant intake may blunt beneficial stress signals needed to activate autophagy or mitochondrial biogenesis. This reinforces the idea that these vitamins are most beneficial when they support, rather than suppress, the adaptive response. In the aging population, or in those with subclinical deficiencies, moderate, well-timed supplementation appears to restore balance without disrupting the cellular signaling cascades that fasting and hormesis rely on. In sum, the roles of vitamins C and E in modulating oxidative stress are not isolated from the broader framework of longevity. They are tightly interwoven with autophagic efficiency, membrane integrity, and mitochondrial preservation. Rather than viewing these nutrients simply as defense mechanisms against aging, they should be recognized as facilitators of the body's intrinsic repair programs. By sustaining a redox environment conducive to autophagy, they help cells clean themselves more effectively and adapt to stress with greater precision. As we continue to refine anti-aging strategies, the goal is not merely to add antioxidants indiscriminately, but to optimize their timing, balance, and synergy to enhance cellular renewal without disrupting its triggers. This more nuanced approach may ultimately help slow the aging process from the inside out, one autophagic cycle at a time.